Well, good morning or good evening, whichever the case may be for you. For me, it's morning and about 6 o'clock in the morning. So if I look a little rough, that's why. Today we're going to expand our knowledge about numbers. We've been looking at working with what are called the real numbers. We talked about integers, and those were a subset of the rational numbers, any number that can be expressed as a fraction, as a ratio. Then there was the irrational numbers, numbers that were non-terminating, non-repeating decimals. Example, pi, square root of 3. When we put those together, we got what we call the real numbers. But that is not all numbers. There's a set of numbers outside the real numbers. And you might think, what kind of number could not be real? Well, obviously, or maybe not so obviously, imaginary numbers. Sounds like the kind of numbers you might find in, I don't know, Never Never Land. But they're not. The imaginary unit arose from, or imaginary numbers, arose from looking at solving an equation of the form x squared equal negative 1. Now, this idea of solving this equation has been around for a long time, and I think the first time it was really addressed seriously was back in the 1500s by some real old mathematician whose name begins with a B, I think. Don't hold me to that. But he looked at solving this equation, and x squared equal to negative 1. To solve this, we would have to take the square root of both sides. So if we do that, take the square root of both sides, I get x is equal to the square root of negative 1. And the problem is, there is no number that has a square root. Let me say that again. I can't find a number whose square root is negative 1. Because this would imply that some number squared is negative 1. Well, it can't be negative 1 because negative 1 squared is 1. So this was thought to be just some sort of unsolvable equation, but this mathematician said, well, we don't have a number that fits that, but we just haven't invented it yet. So he came up with what he called the imaginary unit. He said, I'll make the square root of negative 1 equal to I. Well, a lot of people thought, this is silly, there is no such thing, these are fictitious numbers, but that's what also was thought of about negative numbers and 0 for a long time, until they became accepted and found, hey, yeah, these do have use in the real world. Same case with the imaginary unit. Unfortunate name because they're not imaginary in the sense that they don't exist. They do. Now, the implication, if the square root of negative 1 is I, that means that if I take I and raise it to the second power, I'll get negative 1. These equations, this relations, you need to hold this in your mind when you work with imaginary numbers. If you can do that, square root of negative 1 is I squared is negative 1, you will be able to work with and manipulate imaginary numbers. Now, let's look at I raised to powers. I to the first is just itself, I. I squared, well, I squared is negative 1. We just discovered that, or we're informed of that. To find I to the third, well, I could I to the third, something to the third power, I can write that as something to the first times something to the second, so it's I to the first times I to the second. Well, I to the first is I, I squared is -1. And just like multiplying -1 times a real number, if I take -1 times I get -I. All right. I to the 4th. Well, I can break that up into I squared times I squared. And I know I squared is -1. So that's -1 times -1, which is 1. Okay, not too hard. Now, what I would like for you to do, small assignment, is I would like for you to finish I to the 5th, I to the 6th, I to the 7th, and I to the 8th in the same fashion I was doing here. Use the powers that you know. In fact, after you do that, I would like for you to figure out what is I to the 143rd power. Think you can do that? I think you can. Okay, so that's the imaginary unit I. So we've got these set of numbers called imaginary numbers. And just like with real numbers, we can do operations with them. If I look at combining, adding, and subtracting, I can add i's to I, if I have 2 i's, and I add 3 i's to it. What do I have? Well, it's like adding x's. I've got 2 x's, I get 3 more x's, I got 5 x's, I have 5 i's. Sounds kind of strange to say. So adding and subtracting with imaginary numbers is really pretty simple, just like adding and subtracting x's. Now, when we put the imaginary numbers together with the real numbers, we get a new set of numbers. We call those the complex numbers. And a complex number takes on the form a plus bi. We call that standard form. Might want to write that down. This a represents the real part, and the bi is the imaginary part. Now, any number at all can be written as a member of the complex numbers. Because we took the reals and the imaginaries together, they all fall under the complex. So when I have a number like 6, which we think of, oh, that's just a real number, there's no imaginary part to it. Well, I can write it as 6 plus 0i. Cool, cool. 6 is my real part, 0i is my imaginary part. Now, we looked at adding and subtracting just, quote, imaginary numbers. Oh, really, these are complex numbers, because that's 0 plus 2i plus 0 plus 3i. So, operations with complex numbers, well, let's see what that looks like. Adding and subtracting complex numbers. 6 minus 3i, complex number, real imaginary part is negative 3i, minus negative 2 minus 8i. Again, making the analogy to polynomials, we said adding and subtracting i's is like adding and subtracting x's. It's like adding and subtracting binomials. It's like 6 minus 3x minus negative 2 minus 8x. I would get rid of the parentheses, distributing that 1. I can just drop parentheses. Here I distribute a negative 1, so I'd have plus 2 plus 8i. Now, I'm just going to combine the like parts, the real with the real parts, and the imaginary with the imaginary parts. Negative 3i plus 8i is a plus 5i. So my answer, and this is what we call standard complex form, is 8 plus 5i. What you think? Good so far? All right, let's move on. Multiplying complex numbers. First, let's look at multiplying a monomial, something with just an imaginary part, times a binomial, real and imaginary. Again, it's just like multiplying a monomial times a binomial with x's. We're going to distribute 3i times 4i is 12i. 3i times negative 6i, 3 times negative 6 is negative 18. I times I is I squared, but now I've got a little simplifying to do. Whenever I have a higher power of I, meaning me, not the imaginary unit, want to simplify that. I squared is negative 1, so I get 12i minus 18 times negative 1. Well, that's going to give me a positive 18, and writing it in standard complex form, I get 18 plus 12i. Did I do all the math right? I think so. Let's see, now when we have a quiz over this, if you catch me make a mistake in this video, that will be a bonus point. So, let's see. That was multiplying monomial times binomial. How about a binomial times a binomial? Yeah, let's do it. Just like multiplying binomials with x's, I'm going to distribute. 6 times 5 is 30. 6 times I is a positive 6i. Negative 2i times 5 is negative 10i. And then negative 2i times I is a negative 2i squared. Piece of pie. Now I'm just going to combine, excuse me, before I combine like terms or like parts, I've got a higher power of I. I want to simplify that. I squared is negative 1. So I'll have negative 2 times negative 1. That becomes a positive 2. So now I've got real parts 30 and 2 I can combine. And my imaginary parts 6i minus 10i, negative 4i. Not too bad. I think you're all capable of doing that. Want to look at multiplying two special complex numbers. Negative 2 plus I times negative 2 minus I. We had a word for binomials that looked like this. Negative 2 plus I, negative 2 minus I. What did we call those? Do you remember? Started with the C. What's that, Allie? You're right, conjugates. Kind of freaked you out, didn't it, Allie? I heard you talking. Now, when I multiply conjugates, something really cool happens. With two regular binomials with x's, the inner and outer terms cancel. Well, watch what happens here. Negative 2 times negative 2 is 4. I'll have negative 2 times negative I, that's plus 2i. Then I times negative 2 minus 2i. Can you see what's going to happen there? And then I got I times negative I, that's a negative I squared. These combine to be 0. Negative I squared is negative 1. So I get minus a negative 1. That's plus 1. So I'm just left with 4 plus 1, or 5. My imaginary parts are gone. Of course, I could always write this in standard complex form as 5 plus 0i. Pretty cool stuff. Well, that's something, the idea of conjugates of complex numbers, or complex conjugates. We're going to use that to allow us to do, quote, division. And I say quote because we don't actually do division. We don't actually do long division here. When we say divide two complex numbers, what we're really going to do is make this so that I do not have a complex number in the denominator. And the way we're going to do that, to make this strictly a real number, we're going to multiply top and bottom by the conjugate. Top and bottom because multiplying by anything over itself is multiplying by 1. Multiplying by 1 doesn't change anything. Doesn't change the value of this original fraction. Down below here, well, we found out that the inner and outer terms are going to cancel. All we're going to be left with are the first terms and the last terms. Negative 2i plus 2i is negative 4i squared. Up top, well, now I've got to do a little work. I'm going to have to distribute 4 times 3 is 12. 4 times 2i is 8i. I times 3 is 3i. And I times 2i is 2i squared. Whew. Okay. Now, simplifying up top. That I squared is going to be negative 1, so I have 2 times negative 1. Adding it to, which is negative 2. Adding it to the 12, I get 10. 8i plus 3i is 11i. And down below here, I got I squared, that's negative 1. So I got negative 4 times negative 1, that's positive 4, 13. And we can make this a little bit cleaner. We can make it strict complex form by writing it as 10 over 13 plus 11i over 13. My real part, my imaginary part. Wow, we've done a whole lot. One last thing to leave you with. When I've got division by a complex number where the real part is 0, it's actually easier than this. Because in truth, that's 0 plus 2i. Its complex conjugate is 0 minus 2i, or minus 2i. So when I multiply by the complex conjugate, I can just write minus 2i. Up top, I get 12i. Down below, I got 2 times negative 2 is negative 4. Now I'm going to have I times I, or I squared. So that's going to be negative 4 times I squared, or negative 1. It's going to be positive 4. And now I can divide the real parts to get 3i. Except if that's what you, if this were a quiz problem and that's what you left it as, I would take a point off. Why? Why do you think? Anyone? Anyone? Didn't hear anything. Because that's not standard complex form. So I would write that as 0 plus 3i. All right. Now you've learned, we have learned what it means, what complex numbers are. Tomorrow, we're going to see how do we use these a little bit. Till then, no homework tonight, and I'll be keeping an eye out for you. Get it?